Hello. Um, my name is J Garzella. This is floating point consistency in the wild. And before I forget, I should thank the UROP funding program at the University of Utah. So if we're in the wild, let's take a trip to Chicago, Illinois, to Fermilab, where here we have a gigantic device, and the sole purpose of this device is to calculate the quantity that physicists call the muon G minus 2. And this quantity, like some other quantities in particle physics, has the rather nasty habit of needing to be very, very precise. So today, I'm looking at some code that's been written to try to theoretically predict values like this muon G minus 2. And the thing about it is it matters so much how precise these values are that if the values are off by just a little bit, our best understanding of the universe predicts that like galaxies won't form and the universe will just kind of be a dark pit of nothingness. And so we want to kind of be careful about maybe some of the optimizations we're using, or we want to discover, if we can, the effect that the optimizations that we're having are having on our floating points and our floating point results. So a quick intro to the libraries that we're testing. Here I have about 6 libraries. They're used kind of in the wild by physicists. They're all written in C++ or Fortran. If you notice, I have 2 that are technically the same library. Suspect 3 is a complete rewrite of Suspect 2. One is in Fortran, the other one's in C++. Yeah, and Fortran will come up again. A lot of this high-performance code is just written in Fortran. So let's see. The way that these libraries are generally used, so there's I guess 2 kind of categories that I've divided them into. One is spectrum generators. Spectrum is like something got to do with masses of theoretical new particles and things like that. And so they'll take in the parameters for our physical theory and they'll output the mass of new particle X. Observable quantity calculators, which I sort of have towards the bottom here, are more of the things calculating things like the mass of the Higgs boson for fine Higgs. Or for dark SUSY, they'll calculate the muon G minus 2 that I was talking about earlier. And I guess the thing that is important about these is for spectrum generators, it's kind of an apples to apples kind of comparison between the different libraries. Whereas with the observable quantity calculators, it is they're not calculating the same things. So the way that this would be used is you would start with a benchmark. A benchmark is some parameters, a list of numbers that somehow determine what the physics of the universe looks like. You put them through a spectrum generator. The spectrum generator gives you masses of particles and other kind of important things that you need to calculate observables with, and then you plug that into an observable calculator. And then once you have your observables, you go compare them to what you found with that giant machine that I had on the first slide. What we're going to do is we're going to sort of kind of break this. We're going to break this up a little bit and just test the kind of individual components of this sort of pipeline, so we can see if we can isolate particular errors or particular inconsistencies in specific libraries. So we're gonna take a benchmark that the physicists would use, and then the intermediate outputs will be some of our test cases, and then we'll take a few of those test case outputs and call those our benchmarks for the observable calculators. All right. So really the way we should test this is we have a giant nested for loop, right? For each benchmark, for each test case, we're testing with a bunch of different compilers. What we want to do is we want to compile this whole library, run this test with Clang, with GCC, with ICC, and see what the different results are. And we're worried that the differences between these compilers, or for example, between a different optimization level, you compile it the same code in two different ways, and you got different results, and those different results are going to affect what the physicist would conclude about their paper. And so the tool that does this is FLiT. It's kind of maintained by my lab at the University of Utah. And what the terminology that FLiT uses for this is a compilation. So a single compilation is you choose your benchmark, you choose your test case. For example, a test case would be the muon G-2 quantity. So when you see test case, you should think of a quantity. Then you choose a compiler, an optimization level, and a certain kind of flag or flag, combination of flags. And there's a certain kind of special compilation called the ground truth that after each of the computations has been done, they get compared to the ground truth, and the numbers that we're looking at are the kind of discrepancies or differences in these. So ground truth traditionally is -0 with no extra flags. So doing the least amount of optimizations that you could. So to use FLiT on a library, if any of you all have some high-performance floating point code, I kind of want to describe sort of the process. So to use FLiT, what you first do is there's a configuration file that FLiT has. You just let it know which languages, which compilers you want to use. FLiT used to be only available for kind of C++. With the work that I've done, it's fully working for Fortran, or you could use it for, technically you could use it for any language that kind of gives you .o files in the compilation. That's not too big of a deal. The kind of trouble step is you have to sort of replicate your build system to work with FLiT's build system, so that it can give you that it can do its kind of tricks to compile your program. And it's not that bad. You just put in basically what your C flags, LD flags, etc. are. What's in the works is a capture replay feature where you can run your build system, and then it will use the compiler commands that you've invoked to inform its build system. And then you just call your code, and then FLiT will kind of do the rest. All right. So in the process of doing this, I'm working with code that was written by physicists. They're not computer scientists, they're not programmers, and unfortunately this means that they're not always aware of standard practices for constructing a build system. So for our enjoyment, I'd like to share a few of those build systems. The first one is having no build system at all. The entire library consists of 4 Fortran 77 files, one of which does most of the computations, and it's probably 10 or 20,000 lines long. And the manual literally says, there's no build system here, just compile it. So yeah, that one wasn't, I don't know. So another one is this library decided that it needed to be completely flexible. And in order to do that, they basically reinvented functional programming, meaning this library has a feature that allows you to replace any method that exists in the entire library with your own implementation. It's a little bit of an architecture astronaut thing. And the way it does this is it makes use of the fact that if you compile something with the archiver, with AR tool in Linux, and you have conflicting methods, then the first one in the list of command line arguments, the first .o file that it sees, takes precedence. Versus if you just link it with LD, it'll give you an error. And the last one, and maybe the most fun, is you take all of the source files, you cat and pipe them into a new source file, and then just compile this new source file. So no link time optimization required. So yeah, that one. Anyways, so and there are a few others that are kind of fun, but I guess there might be a place here for some kind of education for people who are domain scientists who need to use kind of high performance code here. So what did we find? I kind of would break up kind of different of these compilations, different of these ways to compile things into kind of two different categories. I deem them problematic and non-problematic as kind of a terminology. A problematic compilation is something that gives you something that totally, completely destroys your results. Like all of the results are now 0 because I put this flag here. That's interesting. A non-problematic compilation is something that either doesn't change the values or changes your values by something that they would still maybe make sense to, say, a physicist who's doing research. And so the thing that we're most interested in are things like that are kind of in the gray area between these two things. If someone who's a scientist is running these libraries and it crashes, and they put in a flag that crashes their program, they're not going to publish results based on kind of things that are obviously wrong. And on the other hand, if things are too non-problematic, if the number of significant digits that's changed is not enough to the level of experimental accuracy, then we haven't affected the conclusions of any like potential research paper. But there are some things that are sort of in the gray area there. Like the big example would be one of them is like there's a certain matrix quantity where you compile it one way, it's one thing, and you compile it another way, and every entry in the matrix has its sign flipped. That seems like it's some sort of an optimization, maybe even a bug. But according to the physicists, this sign flip is physically meaningless. So did the compiler mess up, or did the library just not care enough about what the sign of the value was? So I guess more kind of basic examples of what we found, just things that you would sort of expect. This -PC32 flag on ifort, basically what it does is it changes all doubles to floats. That's a little bit of a approximation, but it doesn't, and this like completely kind of wrecks all of the results that are there. They're off 30 to 40%, sometimes over 100%. And this, I guess, for some reason, these calculations, they need to have a certain level of precision. But for example, when you change between 64 and 80-bit floating points, the results don't change that much. So once you get past a certain threshold, maybe it doesn't matter so much. Another one is a bug that we found, almost certainly a bug, where you have this -f finite math only flag. That flag causes undefined behavior if you have a nan or an infinity in your program. And what's happening is in different compilations, sometimes it hangs, sometimes it crashes, probably undefined behavior. Some of these sign flips things that I was talking about. So so I guess a future direction for these sort of things is to sort of root cause some of these bugs and see if there's actually see exactly kind of parse out within the code of the libraries what's going on here. So for the non-problematic benchmarks, I have a couple of metrics. These are all kind of, the statistics we're looking at are statistics about differences from ground truth. So this is something that compiler optimizations did to this code. And if you I think the thing to comment about these metrics is that the average and maximum difference are going to tell you maybe a little bit more about the data than the other two metrics. Those other ones I think are there just to give you an idea of how the compiler is not kind of world breaking in general. So if you look at just some results here, we see a lot of small numbers and a lot of zeros. So on average, when you compile with something like -F unsafe math optimizations for this certain benchmark, which happens to be rather robust, you get an average difference of somewhere around 10 to the minus 10 or 10 to the minus 9. Now, this actually can be physically meaningful in some situations, but for these particular benchmarks, we don't have the level of physical calculations. We don't have a big machine akin to the muon G-2 that's going to make these differences matter a lot. And similarly for this sort of this other benchmark. And but if we look at, say, a benchmark that is more sensitive, and by sensitive I mean it's one of those physical theories that has less parameters. So variation in these calculations kind of depends on fewer things. If we look at these benchmarks, we see things creep up. We see the maximum difference for suspect 2 is of the order of 10 to the minus 3. Now this is something like if that's the mass of, say, the Higgs boson or something like that, that is something that could be physically sort of meaningful. And as we're going on, the future direction is to kind of understand where exactly those values, what exactly those values kind of relate specifically, and again, see if we can root cause where some of these changes are coming from. All right. That is most of what I have. FLiT is our kind of floating point, robust testing framework, and most of the time, with some exceptions that we might have expected, we find that the compilers are generally doing a pretty good job. They're not contaminating data that much. So we're okay to use things like O3 and -fast math or whatever we have. Thank you.
How do you verify that the O0 build is the correct answer?
So, well, the short answer is you can't. And the reason we choose to use that one, I think, is generally because we don't have a better option per se. So one thing that you can do with FLiT that is, I think, something that we're kind of looking into is instead of comparing differences, just compare the results and then sort of kind of calculate them relatively to each other. The thing is that we're already using percent error here, and I don't think we're getting a lot of bang for our buck in what we're seeing by taking into account that extra data. So to be honest, maybe other compilation, you could almost pick anything. It's just the differences that we care about.
Have you considered, when you're fighting for ground truth, have you considered comparing the results between compilers to say Clang comes up, or Flang comes up with 1, GCC comes up with 2, and the ICC comes up with 1? Well, sort of a voting mechanism or something.
Yeah. And I think, actually, I've kind of glanced at those. So I think the trend that I have seen, in order to first run the computations, we did choose a ground truth. But that shouldn't affect the fact that what compilation, sort of doing this voting process, you can still do that. And I think what I've seen is that Clang and GCC tend to have the same thing when you do O0, and ICC, if anything, either tends to be the same or it might be different. And it's kind of interesting when you look at these, when you look at like which flags changed, because a lot of times it's like a lot of the results are one thing, and then there's a whole swath of flags for certain compilers that change the value by this much and exactly that much. So you can sort of see when optimizations are being turned on and off. And so the ground truth I think that we've been using is GCC, which, although it's technically an accident, yes, I think would go sort of with that voting type of process.
I'm curious if you've thought about doing any benchmarks that have half precision in them. And the reason I'm asking that is because we've found that once you introduce half precision into your middle end, it amplifies the floating point bugs by about 1,000x in my experience.
Yeah. Well, we haven't talked about doing that. Although I think because we're expecting exactly what you're talking about. And I think that for these calculations, even just using single precision instead of double precision can do that. And I think the results with the -PC32 flag are sort of evidence of that. How when we're going, even single precision just isn't enough for some of these computations.